Hello everyone, welcome to the Women DS session. Women DS is a non-profit organization which promotes women and gender minorities in ML and DS. Usha is the chapter lead of Women DS Mysuru and she is also in the India's first Kaggle Grandmaster. And you can follow her on Twitter at urangareju. So this is our team effort and this is our core team behind the event. This is our social media team, Amandeep, Sriram and Yashwant. So join our events for TFUG Mysuru, Vimal DS Mysuru and GDG Mysuru. Join using the meetup group and the links given.
Our community partners for the event are Co-Learning Lounge, Applied Singularity, and Confab. Confab is a unique platform that allows you to host high-quality technical events. You can find the links in the description below. You can check them out. Finally, moving ahead with our event. So, we have a great session lined up for you today. So, we'll start with the first speaker of the day. We have Professor Amlan Chakrabarti with us, and he is a professor at A.K. Chaudhary School of Information Technology at the University of Calcutta. He'll be talking about machine learning for computer vision. We welcome you, sir. Sir, you can share screen now.
Yeah, very good evening to all of you, and thanks to Omen in Machine Learning and Data Science MISO chapter. And I feel very honored to present my seminar to all of you. Uh, so, so as this particular the event or this particular group is focused on machine learning, so I thought that I will present something which is very relevant at the present state of the art of machine learning, which is obviously the application of machine learning for computer vision. So so my talk is very straight, and I will try to keep it very simple so that you can only understand that what are the ways we can use the machine learning for the various computer vision applications. And I will have a very sort of walkthrough without going into the concepts in great details. So, so if you want to know about me, what I work into video analytics and computer-aided diagnostics, and obviously both are pretty heavy based on machine learning algorithms and applications. So, so we so we publish couple of we publish a good number of papers in journals and conferences. And in the case of video analytics, we had a great paper in IEEE VPR last year. And if you want to just have a look into it, I will just tell what it is. So this is actually a this computer uh, machine learning based algorithm, which is based on graph network flow analysis, and which detects the ball positions in a soccer game, and it detects the ball and the player, and that helps us to understand to understand or to estimate the ball position statistics. Okay, so this is one of the work I just gave a brief of that, and you can find the paper, which is generation of ball position statistics in soccer using minimum cost flow network. Apart from that, I am very heavily working in the domain of computer-aided diagnostics. We work with various hospitals in different forms or different modalities of images. We basically do two things. One is the detection, another one is diagnostics. We try to find out the different type of deformities from the different modalities of images like digital X-ray, CT, MRI, and we try to extract information, and from the extracted information, using classification or clustering techniques, we try to also find out the amount of disease or the amount of deformity which has been generated in the particular person. And if you want to look into some of my recent webinars in this domain, you can look into some of the IEEE lectures I have given in the last couple of months. One is on medical image analysis, which was hosted by IEEE Distinguished Lecture Series, and another one was one of the hosted by IEEE Turkey, and that's also how we can use the deep learning in the computer-aided diagnostics. So now, without going into much on my research, now I'm moving into straight onto the topic, and this is the statement what is about machine learning and why machine learning is so interesting, as coined by Arthur Samuels, the father of machine learning. We normally uh, coin him as that. So machine learning means that we will not program the machines the way we normally think, right? So programming the machines means that we have an algorithm. Uh, we try to code it in terms of programming language, and then load it into our system and execute the program, right? So that's called explicitly programmed machines. Whereas machine learning is something which is different. Machine learning doesn't generate programs from that algorithmic point of view. But machine learning tries to exploit the information what is available in the data, right? And tries to learn the system with the data, and that actually generates the model in the system, and that model can be again used as a program in the latter stage of development to try out the unknown data, or to classify or to analyze the unknown data to find the patterns in the unknown data. The other way the machine learning can also be thought about is a sort of paradigm where through the learning, or through experience, the performance of your computation goes, or gets enhanced. So it is something like, as we know that so as a human individual grows from the baby stage to the adult stage. Okay, he or she gets a lot of information from the family, from its education, and from its environment. So by that he or she becomes a very mature individual, very knowledgeable individual when he becomes say an adult, right? So what it means that through experience, a person or a human gets lot of insights, and that gives the maturity to his or her work. So similarly, when we think about a computer program in terms of machine learning paradigm, it is very similar. So what it means that, provided I give you a good amount of data, and the systems tries to work on the data, and tries to find out what is the insight of the data, and through that it develops the model. So more and more data I supply, and more the model works on the data, the model becomes more and more experienced, right? And that experienced model will have a better success, right? Or a better performance, compared to a model which has been developed with a scanty amount of data. And so that's what's learning through experience, and that develops the machine learning. That is the other way of looking into the machine learning algorithms. uh, so obviously what we need to do, we need to have the programs which can access the data, and then use the data to have the learning experience, and then try to develop the learning experience in a sort of model, and try to use that particular model for the data which is still yet not seen, right? For unknown data. And then if we try to make it simple, right? When does machine learning helps us, right? So when does machine learning help? Obviously, we know that there is a pattern, which means that there is some sort of information which is deeply inherent inside my data, right? But which is pretty deep, or which is not so easy to churn out. It is not a simple mathematical equation which I can depict to find what is there in my data. But still, I know that there is some pattern exists in my data. So there, machine learning helps. Obviously, as I told, that I cannot actually generate an equation of a polynomial which has 100 power or more than that, and try to model my function. Okay, that means obviously that will be a pretty complex task. So those type of functions, those type of outcomes, right? Those type of behaviors which we cannot directly put down in terms of mathematical formulas or mathematical postulates directly. Obviously, we know that machine learning can help us. And last but not the least, we have enough amount of data which will be helping us to churn out the inside what is there and try to build my model. So primarily these are the three fundamental issues, or three fundamental components, right? Which gives us an opportunity to try out machine learning to build the systems. And now, if I try to look into that, whether it is easy or difficult, we know learning in humans is so easy, right? A small baby can also know that there are pebbles, there are bumps in the road, there's an animal going in front of that. So it is pretty easy for so slowly and steadily it learns, and it is a sort of seamless affair which happens in the individual. But if we see in the computers, right? If you see computers, we will see that it is not so easy, right? We require so many inputs to my computer, to my program, so that it can learn with the data, and there are different modalities of the data. So that's why learning in an automated world is a pretty difficult task, right? Which is so simple in the biological world, which looks so simple in the biological world. So now let's look into something which is what is computer vision, and we try to look into that, what it is. So computer vision is something which we try to understand, or we try to take the information from our visual data, right? Or the visual data may be image, which is static, or maybe video, which works with a number of frames, which works over a particular timeline, right? And what we try to do, we try to understand the information which is conveyed through this visual data, right? And that's so important. If a computer can understand what are the objects in this particular image or this particular video, or they can find what are the distances between the objects presented in the image, or it can also find out that, hey, this is a full apple, and this is a half apple, right? So these are the things, if a computer can do based on the visual information, then what I am actually doing is I am trying out computer vision, okay, right? And that's the process whatever a brain does through our sensors. So if I try to find that what is happening in a real biological world, and what is happening in my automated computer based scenarios, it is something what I have shown. So there is a sensing device. Okay, we require camera, which is equivalent to our eye. There is a processing zone, or a processing node, okay, which may be some portions of my brain, visual cortex, and some other portions of my brain. So there should be some process or some programs which will be running. Obviously, those are okay. If I am looking into machine learning, there are machine learning based algorithms or programs which will be trying to figure out the data which has been captured through the particular sensors like our camera sensors, and then it will try to interpret that what are the objects in the particular image or a video, what is the environment, okay, what are the other objects in the particular scenario, and maybe pretty more, right? So this is but what are the steps what we have in a particular computer vision process, very similar to a biological process, which means the capture of the information, capture of the image or a video, and then running a process, and then churning out interpretations out of the data which is supplied, and that interpretations will be pretty useful to guide the next state of processes. Like if it is a robotics, then it will guide the robot. If it is a computer in a diagnostics, it will guide the surgical hand of the doctor, or it will help the doctor to complete the next step, right? If it is an automated vehicle, it will try to analyze what are the obstacles in the road, and try to maneuver the star in a busy road. So you see that these interpretations which are very important can generate very important consequences and can drive our systems to take intelligent decisions. So in a nutshell, if I try to look into this, obviously the process in a very simplistic way is something like this. When computer vision and machine learning join hands, what we try to do, we try to train our models using set of visual informations, and maybe simplistically it may be a classification problem where we try to identify objects, and we try to give different types of images of different objects, and try to find the levels out of that using the training data, right? And okay, and then once the model is being launched with a lot of training levels, I can use the model to classify an unknown image which was not being seen previously, right? And provided my training was good, but my prediction for the particular class will also be very accurate by my model. Now, if we look into the different types of computer vision applications, there are a lot, right? And what I have just showing, it is maybe a very small subset of what is that, right? And you can see there are plethora of applications, and each of these applications takes different types of tasks, right? And they may be on the two-dimensional, they may be on the three-dimensional, and there may be fusion, which means the image captured from the different visual forms, or image captured through different types of modalities, spectral modalities, right? So there may be different ways this particular data for each of these applications can be generated, can be processed, and ultimately inference can be drawn. So this is a very simple, this is a very well-known animation which tells that how efficient our computer vision in detecting objects can work. And if you see the levels, see there are levels which are coming out, which are the percent, the traffic light. These are the levels of the classification levels, and they are detecting them very accurately. Okay, some very accurately, some maybe not so accurately, right? So these are the type of applications which we want to build. Now, as we know that machine learning strategies can be of two forms. One is called supervised, and one is called unsupervised. So if you are speaking something about supervised learning, what it actually means that there is a known knowledge, right? And that known knowledge can be considered as a teacher who is supervising his or her students, right? And that knowledge comes in form of a training data which already has the class labels, right? And using these class labels, we try to know the feature of the classes, try to find the distinguishing parameters or features among the classes, and try to find the class boundaries, and try to generate my models which are sufficient to understand the class boundaries, and then the model can be used to classify the data which is not still being supplied, right? But there is a catch here. So when we go for supervised type of classification, especially in terms of image, it means that only the object information by which we have trained the model, for those my classifier can do correct classification. Which means that suppose I have trained my classifier using dog, cat, and a tiger, right? If my classifier is good, whatever images of dog, cat, or tiger is supplied, it will correctly label it, right? But there will be cases that either suppose a bird comes in, or a monkey comes in, right? And then we don't know where it will map. It can map a monkey to a tiger, or it can map a monkey to a cat, right? Based on the similarity of some features. So which is the wrong. So sometimes people actually look into this particular problem in a way that, hey, supervised learning cannot be possible when we have a large variety of my levels, and and we cannot train my classifier with all the levels, right? And then what is done, or the strategy which is followed is called unsupervised learning, which looks into the problem in such that, hey, there is no level. Initially, my model will do a self exploration on the data, right, and try to find out the discriminators in the data and try to differentiate object 1 from object 2 and object 3 from object 4. So by the way, I can separate out, here this is a monkey, which is object category 1, and here this is a tiger, which is object category 2, and this is the cat, which is object category 3. So this way we will differentiate the objects, and we try to form the clusters, and these clusters will normally have the images which are very similar to one another, and by that way we can also identify or detect the categories of the images. So these are the two very baseline approaches by which the object detection or computer vision based strategies are based upon. Now, if you look into the how this ML models can be developed, okay, for the computer vision applications, right? What we can look into, there are ways to develop, obviously, to develop this ML based applications. We require the data. What will be my data, right? So in a very simple sense, the data may be the raw information of an image. We know that what is an image? Image is nothing but a distribution of intensity, a spatial distribution of intensity, right? And the distribution is defined in terms of pixel. So each pixel has a spatial location or a spatial coordinate and will have an intensity value. Okay, be it a grayscale image which only a one channel of information, or be it a color image where each pixel comes with a 3 channel of informations like red, green, blue. But whatever is the case, okay, I can have my pixel as my information, and that can also drive my computer vision. Within the pixel, we can also have some markers which are called the key points, or some of the feature points which can be used as marker for training my machine vision, for my training my computer vision models. And there are other ways. Instead of directly going into the pixel based information, why not we try to extract some features from the raw image, and then try to use those features as my to drive my classifiers, right? And common examples are something like age informations. Common examples are something like shape measures, the distribution, the histogram information of an image, which gives the distribution of the intensity, number of pixels in different intensity levels. That's a histogram, and something like texture measures or a distribution. So these are the primary ways we try to train our models in the context of computer vision. And if you look into the various type of tasks, obviously we know that the tasks may be object classification, which tells that what is that means a particular image belongs to which class of object, right? Whether this is a chair, whether this is a car, whether this is a fruit, whether this is an animal. This is a type of called object classification. Object detection, which means that whether there is an object. So the common problem is the human detection problem. So we try to find out human is a particular class level, and we try to find out whether that particular class level exists in my image or not. So human detection is a very common problem, which is used in a lot of surveillance applications, a lot of other applications, where we try to find out that in all the objects which can be in my given image, whether there is a human. So then what I try to find, it's a sort of segmentation problem where I try to only segment out the human information from the other information. There is something called recognition. Recognition means actually identifying a particular information with a particular already pre-identified pattern. So we have a face pattern of multiple, or face information of multiple individuals. So can I find out that a given face, a face given to me whether it matches the faces which are there in my database, right? You know, the a lot of verification systems like passport verification, criminal records, and lot of verifications in organizations are done based on your photo identity. So what they do, they try to recognize your image. Your computer vision algorithm tries to recognize the image which is given to it, and the image which is already there in the database. Right. Similarly, it can be detecting the particular numbers given a number plate of a particular car. Whether I can detect that, okay, this is the pattern which is X, this is the pattern which is J, this is the pattern which is number 5. So this is something called character recognition. So it may be from face recognition to character recognition. It may be a very long list of applications we can churn out, but fundamentally they're all recognition problems. Next comes subcategory analysis. So can I tell that, okay, this is a human face, but this human face is of type is of X, right? This is a bard, but this is a bard of type X. So within a category, can I find subcategory, and can I? So this is a sort of a mixture of classification and detection problem which is overlapped. So within the class we have to detect something, right? And that's called the subcategory analysis, right? And there is something called sequence data. So sequence data is mostly done in the cases of video. So where we try to what happened next. Okay, what is the correlation between a group of objects in a given temporal instance, right? And so this gives you the understanding the scene, or understanding the or generating the information of a particular scene, what has happened, and that can be analyzed through a video. Okay, so now let us move into after going on to the particular, to the discussing on the various ways or various applications what we have in the computer vision domain, and the way we can look into the problems as the problems which can be classified into different forms. Let us try to look into what is the state of the art way of doing these problems, right? And what I try to that means I will try to pitch into the present scenario of computer vision, which is heavily dependent on deep networks, right? But you can always use a lot of classical machine learning algorithms which are still well used for the computer vision applications, but thinking that the thing which is very much coming into our sphere, which is deep network with computer vision, I thought all of you to introduce this concept in this particular lecture. So what is the motivation here? The motivation here is that we all know that our brain, or our brain network is very efficient on detecting the information which are captured to the visual sensors, right? And why it is? Because it is a very dense architecture. It has a lot of connectivities between the components, though each component is a very simple component, like a piece of neuron. But when the neurons gets connected to the synapses and builds a neuron network, that neuron network becomes pretty powerful, right? And what it can do, it can have the memory, which means that if I have seen a person maybe long ago, right, I can still recognize that this person is X. That means only seeing a half of the person, right? And that's so wonderful in case of our recognition, right? I see my friend, maybe my school friend whom I haven't seen maybe for the last 15 years, 15 or 20 years now. After with age, okay, he or she also have changed a bit, but still I can recognize that this is my school friend, uh, because the memory with some inference works in a very coupled way in our brain network, and that gives us this type of ability to understand the visual information very accurately. And this is also a very simple, very good example, right? That means it is also resilient of the noises, right? So you see that our we can easily recognize who the person is, though this image is very infested by noise. What's the reason? The reason is that in the case of brain network, or in the case of neural network, the decision is not taken based on some input values. Decisions are based on a holistic way. It tries to gather the information from all the neurons and then tries to do a sort of sequence processing of the data, and tries to infer the information in a very holistic way. And that's what is the neuron based processing, or neuron based. And that's why a neuron based processing is so well used in the domain of computer vision. So I will not go into detail. So this is what is a simple neuron looks like. A simple neuron looks like a sort of so architecture, which is something like this. You have a set of inputs which can be from x1 to xm, and there is a special input which is kept constant, and so the input is given 1, and all the inputs are actually are multiplied with the individual weights, right? And this input is 1, so which means that this particular weight is a constant, and that is called a bias, and this gets summed up here. So the equation what we have is that xi multiplied by wi, which is this part, which is this part of my network, where each of the x gets multiplied with the respective weights, and the cumulative sum is done along with the bias, and then this entire stuff goes into a nonlinear activation function, which is defined as g, which is somewhere, which is here, right? And then based on the action of the nonlinear function, the outcome can be evaluated. So there are steps like inputs, okay, weights, then there's a cumulative sum, nonlinearity, and the output. There are several activation functions. The limitations of time, I'm not going into that in details of each of these, but what you have to remember here is that the activation functions are all nonlinear. What that means? Nonlinear means that the slope of the activation function, say this is the activation function, this is the activation function, this is the activation function, all these activation functions, the slope of the activation function is not constant, right? And this activation function, why it's called activation function? Because this actually fires. Firing means a particular activation function that pushes. So this is the input, and this is the output of the activation function. This is true for all these functions. So provided we give an input within a particular range, the output stays in a particular low value. Provided we give the input to a range which is another range, or which is a greater than the previous one, okay, the output value shoots up to a high value. So it is basically also called a switching function, which switches the outcome, okay, either close to 0 or either very close to 1, right? But some of the functions is a sort of continuous varying functions, which has a slope which slowly changes. Okay, but there are some functions like ReLU, which is called a rectified linear unit, where the slope is very a jump, right? So ReLU, why I'm focusing on ReLU? Because ReLU is very much a default function in the case of deep networks, a default activation functions in the many of the deep networks, right? And the way ReLU works is that if you have some input less than 0, that means a negative, it doesn't fire at all. So the outcome stays at 0. And now whatever value greater than 0 we have, the functions get that particular value. So it is something like max between 0 to z, right? So anything lesser than z, okay, yeah, if anything lesser than 0, its value will be 0, right? Anything greater than 0, its value will be the same as z, right? And that helps the network to activate all the values, to generate an outcome for all the values which are greater than 0, right? And I'm telling it's activation because the activation means that suppose you give an input to my neural network, you give a set of input to my neural network, right? And this neural network input cumulatively comes to the activation function. Now whether this particular stuff actually generates an outcome which can be used in the next layer, right? Because what I'm trying to say you is that the layer, maybe there may be multiple layers. So the inputs in this layer, whether contributes in the next layer, depends on the computation of the weights multiplied by the inputs and the outcome produced by the activation layer. So now if the activation layer for this input generates a high value, then this input contributes to the next outcome, otherwise not. So that's why it's so important that whether a neuron, so whether this neuron or this neuron will fire, and firing of the neuron will help to take the contribution from this input to this outcome in a sequence manner, provided this neuron fires. If this neuron doesn't fires, all the contributions to these neurons in the previous stage will not go forward into the next outcome layer. So this is the way the neural network automatically selects and adjusts the data, adjusts the contribution of the input or the features in a layer wise manner, and ultimately evaluates the decisions. So so based on this network, the fundamental the very baseline deep network is called a convolution neural network. And 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 these convolution neural networks are very well are very preferred for the data which are either one dimensional or two dimensional. As one dimensional like audio, and two dimensionals like image or video over the time, right? And we will only stick towards the image here, based on our discussions today. So as we know, the image here is a two-dimensional data. So what happens in the case of a convolution neural network? So convolution neural network, the weight function, what we saw in a simple neuron. Okay, the weight function is being consumed, or is being assumed as a sort of convolution kernel, right? You see the convolution kernel. So how the convolution kernel works? So you see that if these are my nodes in my network, so the convolution kernel multiplies the input with the weights, and it generates respective outputs here. So what I can assume is that these inputs I can always define a sort of computation term in terms of these, that okay, my W0 is something like a cumulative of W0 x0 plus W1 x1, something like this. And if we try to just look into this particular mathematics, I can tell you that this will look like a wet matrix like this, right? And neurons are your input data. So what you are actually doing, these particular computations which are generating y's at each of your node outcome, is nothing but the operation of this particular kernel on this particular node data. Because you see that if I operate the kernel, you will have W0 x1, W0 x0, W1 x1, like this. We can go on and go on. So the convolution kernel is nothing but the same assumption of the neural networks which were there in our 1D dimension. Instead of that, it becomes a two-dimensional data, works information, and tries to convolution do. Each of the convolutions tries to extract one property of your image information, right? And then there are several stages out of that. Then there is a subsampling called max pooling, just to reduce the convolution filters, data which comes okay, flatten the data just to drive my classifier. So the convolution neural network, in a summary, consists of a series of convolution layers which tries to extract the information at every stage. And these informations may be something like this. That means you can look into the gradient information, the simple edge information at the first layer of convolution. Then you try to find the connected edge in the next level of information. Then you try to find the connected regions in the next layer of information, and slowly but steadily you go higher up in the ladder to classify that particular object or the particular information which is supplied in your image, right? And this is a very simple example by which you can classify a particular handwritten image, a handwritten text image, whether it is which number it tells it, right? And this classifier depends on how many object classes you are trying to you are trying to use in this particular model. For the handwritten numbers, as the number of classes are 0 to 9, you have 0 to 9 levels. But if you think of the standard of the very well known image classifiers, like ImageNet or something, you have something like 1000 class levels of the images. I'm not going into further on this. I will just touch up in the last this another beautiful network which can also give a very great role in capturing the images, and that is based on recurrent neural network. I will not go into details of this. Only I will tell you that a recurrent neural network, unlike a normal neural network, it just doesn't put out which is a parameter which is called H3 and tries to use that back with the current input to predict the outcome. So your current hidden state is nothing but a weighted computation of your current input and weighted combination of your previous input state, and then there is an activation function which works on that, and then on this there is a weight function which produces the final outcome. So what is the difference? The difference is that this particular y2 not yt not only depends on the current input xt, but also depends on the previous outcome. So what it means is that if you are trying to make a sort of correlated outcomes in a sequence, that okay, in the first sequence I find this is A, and the next sequence I try to find this is M, and next sequence I find it is a L, and I then I prepare the word Amlan, and I know that this is what is Amlan is.
So you're cutting up.
Very easily, yeah. So this is, I will just show you this example that how this works here in the case of recurrent neural network, how you can just try to detect a particular scene, image captioning, and there's a very beautiful example, and not the details of this due to the limitation of time. Just see that using the neural network, you can see very simple way you can do so. So in short, this network will try to first of all extract some of the features using the standard convolution neural network, and then it will process the outcomes in a sequence using an RNN, and will try to develop the captions. So this is also one beautiful example of image captioning, and you see that pretty good applications has been developed which tells about image captioning in this recurrent neural network, right? And obviously it is not that everything works good. There are some failures also, right? And so I end up here. So why to try to discuss with you what I tell you in my lecture is that I try to show you what are the different applications what we have in the machine learning domain, and then we try to tell you about some of the very popular deep network based algorithms or applications which we can apply for computer visions. And thank you all. If I have any questions, I will be fine to answer that. Thank you.
Thank you, sir, for your insightful talk. We got to learn a lot from you. So do we have any questions for Amlan, sir? I guess no. There are no questions for you,
Okay,
sir.
okay, okay. Thank you all. Thank you all. Yeah, thank you.
Thank you, sir. Thank you.
Yeah.
Okay, so next up we have with us Julian Sara Joseph. She's working as a software engineer with Fractal Analytics, and we also have with us Karthika Kamath. She has just completed Plaksha Tech Leaders Fellowship. They will be talking about COVID 19 data visualization and modeling. We welcome you both.
Hi, can I share my screen?
Yeah, go ahead.
So, welcome everybody. I know it's very late for a Sunday evening, but thank you for joining us. Our talk is going to be on data visualization and modeling. For any one of you who might be new to data science, if you want to get started with any data modeling or visualization, I'm hoping our talk will help you guys there. A brief introduction on me, like Srishti just shared. I graduated as a computer science engineer in 2016, and since then I've been working as a developer, as a full stack developer now. And I've been a Women in Data Science ambassador since 2018 for the city of Mumbai. So we have regular conferences every year, and you can find me on Twitter by this handle or on Medium, where I like to write blogs. Um, I have,
Hi,
yeah.
hi everyone. So I finished. Sorry, am I audible properly?
Just a second, I'll go on mute.
Yeah, I was saying, even I, along with Julian, I'm an ambassador of Women in Data Science, Mumbai, and I just completed Laksha Tech Leaders Fellowship. You can find me on LinkedIn and Twitter. Like Julian mentioned, we conduct this this webinar every weekend. So this is the lineup of these are the different variety of talks that we had in the month of June, July, May to June. So we started in the month of May, then June and July, and we have our last final two talks in the next weekend. So if you're, you could follow us on different social media. So YouTube is where we'll be hosting all our live sessions. And Instagram, we also have our podcast. We just recently launched that. It's called Data Science Sagas. It's on Spotify. And Medium, we write blogs, and Facebook and Twitter. So all of these places you can find us, and about Wiz Mumbai. So we are regularly hosting a lot of live sessions. About today's session, I think Julian, you can carry. Yeah.
So, with that brief, let's get started with our agenda for today. I'll be dealing with the first half of the talk, that's data visualization, and Karthik will be taking data modeling for you. So here is the collab. I'm hoping all of you are familiar with Google Colab by now. We are now into our, I think, the 4th month or the 5th month. I've lost track of how many months we have been living in a pandemic, locked in our homes, overwhelmed with a lot of data on, of course, COVID. So if you guys, like me, are optimistic and like telling stories with data, this talk is supposed to help you plot data with all of that COVID data that comes up in the news that you keep reading on every blog, every Instagram, wherever you read news from. So let's try to plot some charts from that data. And if anyone's new to data visualization, I would like to state it as I break it down into just 5 steps. So firstly, like anything else in life, have a goal. What do you want to actually present as the objective of your story? So once you have that in mind, like maybe you want to say, present the most number of recoveries in a state, or if you are living in Mysore and you have seen the trend the number of cases have decreased every time you have a strict lockdown, or maybe it keeps increasing when you have a relaxation of the lockdown. So have that objective in mind. Once you have that, the second step is to find a good data source. And this is very important because you need to make sure after you've put in so much effort in building the visualization, you don't want to be called like your data source itself is incorrect. So make sure it is an authentic source. Then you might have to so currently I'm going to focus on just Python, but of course you can plot using, there are n number of libraries out there that help you plot these charts. If you were to have used JavaScript, there are high charts, AM charts, to name a few, d3.js. But here in Python, we're going to use for today just matplotlib, pandas, and a library that's called Plotly Express. A very fun library. Once we get into that, you'll see why I'm saying that. Now, once you have the library in place, the next step is to actually convert whatever data that you have into the format that the library requires. So very often what happens is you might have to make changes in your data, the way you've gotten the columns. Maybe you might have to pivot your data frame, or you might have to add columns. And whatever has to be done for the library to make sure that this is being plotted, you might have to make those transformations for your data. And finally, go ahead and plot it. So for today's talk, we're going to focus on these 7 charts. There's line chart, tabular data for those who like it, bar charts, 3D plots, and then we'll move on to maps. So line charts, basically, they might seem a bit tedious, but they do give a very good picture in one go. So what I've done here is I've used a data set here which looks like this. So pandas, it's very easy to read any CSV that you have. I've downloaded all of this data, and in Google Colab, all you need to do is load your data from here. You can just load it from wherever you've stored it, and you can copy the path and give it here inside read CSV. So here currently, this is a notebook that has already run in order to save time. Whatever data is there inside the CSV is converted into a data frame, and this data frame is being plotted here. So it makes it easier for you to understand. We have confirmed, recovered, and deaths being recorded for all the countries of the world since January till I think this is there till July. And what we need to further go on is, so we're going to plot a chart. Our objective of the chart here is to plot a line chart for just 4 countries, so that we can try to find out what has the trend been in these 4 countries over these period of over a period of these months from January to July. So let's see. This is how I've reduced my data frame into just 4 countries: UK, US, China, and India. You can move on and maybe go ahead and find out what is the population for all of these countries. Like I found out, this was basically just Googling population of UK, US, and India and China, because that'll help us reduce it into a relative format. Instead of seeing these entire numbers as it is, I am now converting and creating this data by using these populations. And I've also decided to use 4 different colors for these 4 different countries. So I have a colors dictionary, which is mapping different countries to different colors. Now in matplotlib, so currently I'm going to use the pandas dot plot, but I've also imported matplotlib. If you had noticed, that is basically so that we can actually give this style. Now, if you have noticed magazines, if you read magazines like Economist or New York Times, they often have charts that look really fancy, and they make use of this style that's called 538. I would really recommend you go through the entire website on how they offer so many different styles. So I've used matplotlib only to make sure we can add that grid, that styling inside the chart, just to make it look good. And here, as you can see, I've used pandas dot plot function, which can make plots of any series or data frame. So Google Colab does this, which is very helpful actually. If you hover over any function, you can actually see what is that function going to do, what are the expected parameters, and so on. Some of them might be optional, some of them might be required. So it's an exhaustive manual, so you can go through and find out what all things you can do. So here I have the data frame that I had actually taken above. I had now named it as COVID. See here, I call it COVID here. So I'm plotting that right now. And I can go ahead and call, what I've done here is I've used this, the colors that I had chosen above, the data frame that I've used above, and I've also made sure that our the y-axis is in a human readable format. So I've again made use of matplotlib to convert the format here using the ticker function. So that's it, and we can make our canvas prettier by adding titles, labels, and ta-da. So we have from February till July, this is how the plot has been for all of these 4 countries. So here you have the cases for every country. Moving on to our next plot. If we used pandas there to plot, we can make use of matplotlib. Here I've again used the time series data. Also, if you want to upload your data into the drive, you can run the moment you click on this drive icon. You have this cell printed out. I've mounted it right now. There is a very intuitive way of mounting this. You have to enter a password, and that can be done. Once you've done that, you can make use of your data that you have uploaded in your Google Drive like this. Like I have content drive, my drive, and I've used whatever data I had stored in the Google Drive. So that's another way you can access your data. So here my data looks like this. You have total confirmed, daily confirmed, total recovered, daily deceased. It's a time series for a lot. I think this is India, but let's see. Yeah, so again here we are moving on to plotting a line series. Yes, this is the really confirmed for India. So in matplotlib, along with plotting a line chart, we can actually go ahead and use annotations. So here all I've done is plotted these lines. So we have data for a lot of dates. So I've actually reduced it by using an ilog here, and we'll be plotting just. So the plot is very simple. Again, hover over this, you can find you have to give values of X and Y, which is going to be your dates. So your 31st March, I hope this is visible, 31st March to 13th of May. So here, by this function, I was able to plot this all over. But if you notice, I also made use of a for loop so that I can actually plot the y-axis value. And that is what you're able to see here. Like what is printed on this, 609 was the value of cases on this. So annotations are also a wonderful way of making sure your visualizations are telling the story that you want to. So here, there are more annotations that I've added that actually say on the second lockdown that was declared on the 15th of April, you had a decrease. Or you can go ahead and, apologies, you can go ahead and plot it on any point. Here it was the day 47 of lockdown. So make sure you have fun playing around with this. You might find some trouble trying to get the axes correct, but once you get the hang of it, it's very simple. So any data set that you have, any X and Y columns that you would like to plot, and give it a beautiful background. Like I'm sure a lot of you like dark themes, so that's why I've chosen to give in the canvas color as black. Moving on to the next plot. So actually I tried to go ahead and plot it for any. So what I did was I used the same data set that we used initially for the countries. I reduced it to just one country, say Sweden, and I ran the same functions, gave the same data, and here we have it for Sweden, how it has gone from June till July. So basically, I'm trying to show that any data set that you have, you can plot it using matplotlib in the way you want it and annotate it. Moving on to the next chart, we are going to bar chart. The visualization here is going to be based on district level data. So here we are focusing on the state of Maharashtra. I am from Mumbai, but I tried to find it for Mysore. I am sorry, due to shortage of time, I couldn't find it for Mysore, but it will be definitely applicable for any data set that you've used. Here, what I'm trying to do is plot. So if I was to do the confirmed, disease, recovered for everything, if I had to plot a line chart, it would be a tedious task. That is why I'm trying to now focus on telling the story in one go by plotting a stacked bar chart. So I don't have to plot three different line charts here. You can sure do that, but in order to tell a story quickly enough, here is one look at, in one look, you can actually understand which district is having the worst scenario currently. So here it is Nasik that's having the maximum number of confirmed cases and the minimum number of recovered cases. There are no recovered cases. So here what I've done is I took out all of these columns in different variables, recovered, deaths, and confirmed. I was coding this really quickly, that's why it's named ready and co. But it's very similar. Matplotlib helps you again choose the grid lines, the ticks, the labelings, x-axis label, the y-axis label. The drill is very same, but here I would like to focus on just one small note. Red and green, for any of you who are going to be presenting visualizations, please try to see if you can make your charts don't have the combination of red and green if you want to make your charts colorblind friendly. So red and green is usually not colorblind friendly, and you can make use of blue and orange, that's usually suggested. And if you want to go ahead and read further on what are best colorblind friendly palettes, I will share this link ahead. And because what you might be seeing as deaths and recovery might not actually seem like that for a person who's suffering from color blindness. So what's blue and red here looks like this for a person who is not able to see those colors. So why not make it a inclusive visualization? And if I were to just run this again, just a second. So here you have it. There's no red and green here, which was disturbing for them. Sure, go ahead and you can change the whatever I've named here as red. We can change that into blue or orange. That is still visible. And this gives you a quick story to how COVID has affected the state of Maharashtra, district-wise. Now, some of you might actually prefer seeing numbers directly instead of seeing them on labels and hovers, tooltips. So for those of you, I have just basically tried to show that pandas, if you have loaded a data frame, you can just style it by using this very quick function that is background gradient. You can give a very simple color so that you can focus on what is worse and what is not, because we're all visual beings. But I am not somebody who enjoys looking at tables and numbers directly. So that's why I'm going to introduce you to Plotly Express. FYI, if you want to actually install any library, this is in Google Colab. You can just do it using pip install within this directly. Here, I've used the same data set that I've used above, and I showed you a table out of that. What I've done is I've created a 3D scatter plot of confirmed, recovered, and deaths that you saw as tables, as columns of a table. Here you can see it in a 3D format. So you have deaths, unfortunate ones, and the confirmed cases. It's fun enough to see it like this. You have a total, we had a row that said total, so that's why it's on the very top. On this part, we have Maharashtra again, and it's there for every state. So the color of the state is what I've given as your index. And there's one fun thing that you can see is, okay, let's do it for Karnataka. Sorry. If you double click on one particular state, everything else can be hidden, so you can focus on just Karnataka. And here you can see it in one quick go in a 3D format, the confirmed, the recovered, and the deaths. So that's Plotly Express. It has amazing amount of functions for plotting different kinds of data. This is just one thing that I've shown. We'll move on to other things that you can plot. So just like we plotted using Matplotlib, a bar chart, we're going to try doing it with Plotly Express. In Plotly Express, again, we're using the same data set above, but here I have tried to transform the data in such a way that I can actually make it relative and find the daily number of deaths by who are active cases, which are the recovered ones. I've just added a few columns in addition, and created a very, because we're doing this again and again and again, it's always best to create functions. And this is what this the objective of this function is, to be able to just, you tell me which column you want to print, what color do you want to give it, and then I'll print this bar chart. So if you are doing this on a repetitive basis, go ahead and write a function for it. Px again is the Plotly Express. Dot bar chart will help you plot a bar chart. Again, hover over it, find what are the required arguments, and here we have total active cases. So I can do it for any column. There are total recovered cases. I can just pass total recovered, what color I want. I've used black here. So here again, on a daily level, we have cases in India have been rising, which is not surprising. If your data set has data for say July and August and coming months, it'll just keep on getting added here. So your functions and all would be intact. Just make sure that you change this data set that you're sending here. Again, I have plotted here another. I've used the same function, deaths per 100 recovered, to show it in a relative way. So that's it from for Plotly Express. Finally, we are now moving to a global level with, where we have maps. I have loaded the John Hopkins University's data, where we are able to see it for every country, and I think this gets updated on an hourly basis, like every 2 hours it gets updated. I've just made sure that I've used the same, I've renamed the names here for ease of access below. Here, Plotly Express has given us the ability to plot this for the entire world, and we can, of course, choose what colors we want, how many dates for how long do you want to show this. So here is the plot that looks like. I'm sure you might find these scatter plots, you can modify it, but some libraries come with their limitations, which is why people try to go write their own libraries. Feel free to do that. Here is another world map, where this is a chloropleth map, that was a scatter plot map, world map, where again, here we can choose what colors to give for every country. If I were deciding what color gradients to use, I would go ahead and provide that in my color scale. This is a chloropleth map, as you can see, and I would have to switch the auto color scale and the reverse color scale to false if I were to use my own color scale. Then that would change the entire gradient look that you have here. So that's it from my side. I have a blog version of this talk in Medium, so feel free to go ahead and check that out as well. Since we are on short on time, these are the resources. I'll be sharing this notebook with you for future reference. Over to Karthika.
Yeah, ma'am, we have a lot of questions for you.
Sure.
Yeah, so firstly, they want your collaboration. You'll be sharing that later on.
Yes, I will be sharing all of sorry. So I will be sharing all of the notebook, the resources, all of this. So no worries on that.
Yeah, Alan, there are some questions. I'll just pop them up.
Sure.
Yeah. What is sticker here? Please explain it.
So Matplotlib allows you to, if you're referring to the Matplotlib ticker, this helps you use so you might have decimal format of data. You might want to reduce it into human readable format. So supposing you have it in 4.3K, that is not really understandable by everybody who's viewing this chart. So those ticks that you see on the plot can be convert it into the format that you want to see. Maybe you want to see it in thousands, so you can actually change that. It's that I'm guessing this is that ticker that he asked.
Okay. And we have another question. We usually import Seaborn and Seaborn.heatmap representation. May I know the importance of that and the difference in matplotlib and Seaborn, which would be better?
Okay, Seaborn is coming in the next segment of this talk, and the difference between this, it's based on your use case. So that every library comes with its own advantages and its own cons. There are some libraries that have limitations on certain parts, but here I think she's focusing on heat map. I'm sure Karthika has used Seaborn in her talk, so she can give more details on that. But what is better?
So I think
based on, yeah, Karthika, go ahead.
Yeah, I was just saying, Matplotlib and Seaborn, both are used for plotting equally, but Seaborn is comparatively easier to use and a little more friendlier. You have a lot more varieties to do in that, like heat map and all of that can be done better in Seaborn. And I'm not sure, but I think Seaborn is a high-level API and it uses MATLAB somewhere in the backend, I guess. Matplotlib, sorry. Why am I saying MATLAB?
Yeah, so it completely depends on the person who's using this. Whatever is easy for you, whatever you find useful, or something. Some things might be irritating for you guys, and you might want to use a different library. There is nothing stopping you there.
Yeah, and the last question, where how can I debug in Collab? How can I run all code at a time in Collab?
All code. I think there is a way to run all code, all the cells together. Debugging is very easy here because every time you have an error, they actually give you the option of search in Stack Overflow directly, where you just have to click the button and it actually Googles it in Stack Overflow. So the stack trace is is visible to you, and you can actually go and find out what the key error is, what the value error is. So the stack trace comes if you run a cell and there is an error in that cell, it comes up just below that cell itself, and you can go ahead and find out what is wrong in your data set, or maybe you forgot a comma, or you forgot to complete the parenthesis of that function.
Yeah, Vikas, tell me.
Yeah, I think that's it. Thank you, ma'am. Yeah, Karthika, ma'am, you can share screen.
Yeah, I've shared. You can add that to your
Yeah.
screen, maybe.
Yeah.
The screen is visible,
Yeah, it's
right?
visible.
Yeah. Okay. So now we, like Julian talked about all the visualization, so all the storytelling and all of that. What else you can do with the COVID-19 data or any data? I mean, here I'm talking from the point of an epidemic. So here we'll be using itself. For this, first of all, I'll start with, and just to answer the previous question, how to run all the cells that I'll just show you. Yeah, so here there is this time and run all, so that can help you run all the cells. Anyway, so coming back to the top, first of all, we'll import all the libraries, necessary libraries. Here there are libraries. I'll just give you what all I've used. There's this library Optuna, which is not there in Google Colab already, so you'll have to pip install that first. And this library is for hyperparameter optimization.
Ma'am, sorry to
There are.
interrupt you, but you're breaking. Your voice is breaking.
Oh, okay. Is this okay? Any better?
Yeah, it's fine.
Maybe I think am I sharing my video? I'll stop my camera. Yeah. So, so I will say, first of all, we'll be importing all the necessary libraries. I've used Optuna, which is a hyperparameter optimization library. I'll talk about it when we use it. And wget is a library which is used to, fetch things from different web API, web services. So here we are using that because you're going to use Kaggle dataset, and we'll use the Kaggle API. And then the other libraries that I've used is, again, for plotting, I've relied on matplotlib itself, and then NumPy, SciPy, on all of these things, which are fairly commonly used libraries. There are something which this can be something new, which is FB Prophet, and this library is used for time series data analysis and forecasting mainly. So here I'm using that in order to understand the trend in the COVID-19 data set. So as when I use the libraries, different libraries, I'll talk more about it. Coming to first the theory part of what I'm trying to do over here. So for any infectious disease, like we know, infectious disease is a disease which transfers from one person to the other, like COVID-19 also. And so there are certain questions that we can ask, that how fast is this disease spreading, or what is the recovery rate? So different kind of rates, like are people dying, all these different rates. So like we are still, asking these questions for the current COVID-19 situation as well. So how do we answer this? In a broad sense, these epidemic models, called like compartmental model, help you to give an idea. So why is it called a compartmental model? Is because it divides the entire population into different compartments. So the different compartments start with, like, a very basic compartmental model is the SIR model, where S stands for susceptible, I stands for infected, R stands for recovered. So the entire population will be dividing into these three subgroups. Sorry. So on day one, let's say, or day one of the infectious disease, let's say there's only one person who is infected, and he's a person who is potential, to transfer the disease to others in the population. So the number of people into different compartments would be, and also let us take an example that the population consists of only 1,000 people. So susceptible compartment will have 999 people, and infected will have this one person, and recovered will be 0 on day one. So this is the idea of how you divide the entire population into different compartments. And what we are trying to do using this model is to understand how different people move from one compartment to the other, like how people are getting infected. So when they get infected, they're basically moving from susceptible compartment to the infected compartment, and as they get recovered, they move into the recovered compartment. There are a few notations to keep in mind. Capital N is the total population. If we take India as the example, then this capital N will be something around 13 or 14 billion. And S of T is the number of people susceptible on day T, because it's a function which changes with time. So every day the count changes. So that's why we'll be seeing with respect to T, which is the time. So, and likewise, I of T is the number of people infected on day T, and R of T are the number of people recovered on day T. Beta is another parameter which we have to estimate. So beta is basically expected amount of people an infected person infects per day. So which is, in other words, contact rate. So to explain a little bit more and give that intuition, like I've written, let's consider the probability that an infected person infects a susceptible person, 25%. So, for example, if there's one person who is infected, then that person, the probability with which this person will transfer the disease to another person who is from the susceptible compartment will be 25%. That is an assumption. And let's also assume that on a single day, this infected person comes in contact with 4 susceptible person. So in total, the net, what is the beta value? That will be 25% into 4. Like one person is affected with a probability of 25%, and likewise 4 people are coming in contact. So that is why 25% into 4 gives us a net 1, and that is That is what is a beta value. There's another parameter, capital D, which is the number of days that infected person has and can spread the disease. So let's say it can be a week or two in case of COVID-19. So that is the number of, that is the, like, let's say 14 is the capital D value. Then gamma, which is proportion of infected recovering per day. That is, so let's, so again, infected person, let's say that person has a disease for around 14 days. So capital D is 14. And inverse of that, 1 by 14 is gamma. It's basically a simple cross multiplication. So one person has a disease for D days. That means after D days, that person is recovering. And in how many days this person, I mean, in one day, how many will recover? So that cross multiplication gives that 1 by D. So 1 by D is nothing but gamma, which is the recovery rate. Then this R naught is reproduction number, which is something a lot of you all might have heard in the COVID-19 situation also, that R naught is the total number of people an infected person infects. So gamma we saw on a single day. So R naught is basically how many people get infected in the entire duration of that person carrying that infection. So that will be beta, which is the contact rate, into capital D. Capital D is the number of days the person has the infection. So, and D is also 1 by gamma. So in nutshell, R naught is beta by gamma. So it's basically, if you have these values, these two parameters, if you know these two parameters, beta and gamma, you can find R naught very easily. Same thing. So these things, when I put into the visualization, this is how they are related to each other. So yeah, so the three compartments that I told about, S, I are susceptible, infected, and recovered. The arrow shows the direction in which people move from one compartment to the other. So from susceptible, people will move into the infected compartment, and from infected, the people will move into the recovered compartment. This is a very basic model. And so how is the relation between the movement? So the rate of change of the susceptible compartment, which is ds by dt, is minus beta into I into s by n. To explain this, like I told you, let's consider, for example, beta as equal to 1. So one infected will infect one another susceptible. So beta into I, that is basically. So one infected I into beta, which is we are assuming as 1, will be the value. But here, but we don't know that this person coming in contact with the other person is falling in an infected compartment or recovered or susceptible. I mean, we don't really know that that person already has the infection, or is that person recovered, or is it susceptible. So that is why we'll have this another ratio, that is from the total population, the susceptible part. These are the people, when the infected people will come in contact to, they will be the ones who will be catching the virus. So yeah, so that is why we have S by N as well. And that is why ds by dt is, the value is beta into I into S by N. But we have this negative sign, which is very intuitive. That is, the people are moving outside the susceptible compartment. So when people are moving outside, it will be negative, and the same value is going inside the infected compartment. That is why it's going to be a positive, same value into I into S by N with the positive sign. And from infected compartment, there is some fraction which is getting removed and going into the recovered compartment. That is why that thing, value will be getting subtracted. And what is that value? It is gamma into I. Gamma is the recovery rate, like I explained before. And that same value will be getting added into the recovered compartment. That is why it is with a positive sign. And all of this is rate of change with respect to time, because we are dealing with a time series data. Every day, this data changes. And the interesting part is, for the compartmental model, you are the designer. I mean, you can have your own different compartments. So you can have a compartment which is caged or by separated. Like you can have a compartment where people above 60 can fall into a different compartment, or you can also add other compartments like quarantine compartment or asymptomatic patient compartment. So this way you can obviously add more compartments and make the problem a little more complex. But as you do that, you get better results also. So you can design the problem better. And to give one more example, I have added two more compartments, which is exposed and the fatal ones, or the death one, which is commonly used, or that compartment is also very popular. We've seen a lot of models with these compartments. So by adding these compartments, the other parameters that gets introduced are E of t, which is the number of people exposed on day t, and D of t is the number of people dead on day t. So when I say exposed, what I mean is, what if a person gets this infection, that person doesn't really show symptoms on the very, as soon as the person gets infection. There is some incubation period, after which that symptoms start showing up. So that period in which that person is having that virus, but not really, showing that symptoms, that is the incubation period, which is given by this exposed compartment. So people having these kind of things will be falling into the exposed compartment. So how the relation changes will be from S to E. The relation is the same. What changes here is E to I. So from exposed to I, we introduce another parameter called delta, which is the length of the incubation period. So that will be introduced, and the change is delta into E. And another change we can see is the dead compartments. From infected, people can either go to dead or the recovered. So when they go to the death compartment, that time the relation is introducing another parameter here called rho, that is the rate at which people die. Like we had in the case of recovered, rate at which people recovered, which is gamma, is equivalent to that in case of death, which is called rho, that is rate at which people die. And another parameter that we'll be introducing is alpha, that is fatality rate. And if alpha is the parameter where people go from I to D, then 1 minus alpha will be describing I to R. So these are the changes that will happen. So you can see how adding more compartments will add more and more parameters to your model, and things can get a little more, complex. So same thing we write in the equation format, and these equations are called ordinary differential equations, ODE. So the same logic, if the arrow is moving outside a compartment, the sign will be minus, and if it is moving inside the compartment or is directed towards the compartment, then it will be a positive sign. So keeping that in mind, we can write the equations, the ordinary differential equations. Okay, so how do we code this now? First of all, the way I'm doing is I'm defining different functions for different things, and I'm calling the functions. So the first function is plotting this, and for plotting, I've used matplotlib itself, and it's a simple plotting function. There's nothing fancy in this. We are just going to plot these values. Then there is deriv function, which is what we saw. These things, these mathematical equations, we'll be just writing it down into this function, because we need to know that, we need to let the model know that these are the different functions that we are supposed to solve. So we'll be writing that as it is. And the argument will be giving all the parameters which are to be estimated, like a beta, gamma, delta, alpha, all of these parameters that we used, will be giving that as an argument. And y is a list which contains all these values, S, I, R, D. So all of that, and these are the ordinary differential equations, which will be just writing it as it is and returning these values. And these values are basically with respect to time, how these values change. So now how do we use this function and all of this? So first of all, this is just an example, and I've used only hypothetical values over here. So all these things, like capital N, which is the total population, I just hypothetically used it as 10 lakhs. Then D, which is the incubation, I kept it as 4. Gamma, delta, R naught, all these values I've defined on my own, and these are totally hypothetical values. So initial condition is also something which we have to define. So on day 0, these values would, so infected, recovered, and dead, all these compartments will have 0 number of people. There will be only one person in the exposed compartment, that is why this is 1. And S naught, which is the susceptible, will have the rest of the population, which is N minus 1. We also have to define the time period. So we'll be using this numpy function called linspace, and we'll define the time period. So we also have this initial condition, and we'll produce, all of these values will give it to the y naught as a vector. That is what we'll be giving to the function. Now the function that we have used is ODE int. This is a SciPy function. So to solve this ordinary differential equation, we just need to use this ODE int function, which is available in the SciPy library. And this really solves the problem. I mean, it's very daunting to see all these mathematical equations, how to really solve that. But this function really, I mean, it's as simple as using this function. What we have to do is just feed in the arguments. So all these parameters that we have defined, or hypothetically defined, we'll be providing that. Also the time period, the initial condition, as well as the ordinary differential equation, which is then this function derivative that we had defined over here. So all of that is given to argument, because it will return, although with respect to time, how these compartments, the number of people in these compartments changes. So now we have these values. What we can do is we can plot and see for ourselves. So that is where we'll be using the plot function, and this is how it is. So on day 0, if you see, there'll be like, if the entire population, this blue line, this blue curve, that is maximum, and everything, rest of the curves are 0. And as the day moves, this susceptible curve comes down, and we see the peak, a peak happening in the case of infected count. So when we talk about flattening the curve and all of that, this is the curve that we talk about, that this infected peak which is coming, we need to flatten that, so that hospital is not overburdened, because there are only limited resources available. So yeah, that is about this, which is the epidemic. This is the compartmental model, and this is how you can visualize the case or forecast or see what is going to happen potentially in future. Now, to take examples of this second part, I'm not going to go in depth of this because it just takes forever. There's a lot of things involved. I'll just go overview. I'll be sharing this Colab link so you can check for yourself later on. Here, I'm using the India dataset. Because like you saw when I was explaining, I use hypothetical values, but now we need to have some concrete values. So we'll have to use India dataset. And for that, I've used this Kaggle. I've shared the link here. This Kaggle dataset is what I'm using. And I'm using this because it's so it's again fetching dataset sourced from various other places like the Johns Hopkins. They maintain a dataset. So that is what they are. This Kaggle dataset is also doing. Yeah. Okay. So how do you load the Kaggle dataset into the Google Colab? There are a few lines of code that will help you do that, which is over here. What you just need to do is go to the dataset, and you need to have your username and the token. So how do you get that? So when you create an account in Kaggle, and you go to this my account, yeah. So over here this thing called create new API token. When you click that, file will Kaggle.json file will be downloaded, and that will have the user key. So you can just copy paste that in this. So username, mine is Karthika Kamath, and key I have erased for now. So you'll have your own key, but you can paste it over. Then you can just follow these lines of code. And another thing is this particular thing. This is the API which you can get this. Yeah, so here, this is the data set, this three dot, and copy API command. So this is nothing but the same thing, this thing. So you can paste this, and this way that data set will be downloaded, which you can unzip, and then you can finally use it. And when you unzip, basically it is going to be there in here. You can see all the data coming up over here. Okay, so um, so let's see what the data is. So we are going to use this data CSV file. We'll just see the tail of it. So what this data consists is, I mean, it consists of all the different provinces, different countries. So all over the world, the data is there, and the values, the count is confirmed, death, and recovered. But we are just interested in the India data set. So we'll have to do a little bit of manipulation on this data and just, extract only the India data set. So that's what I've done over here also. And when we see the India data set, what I observe is that until June, every date had only one particular entry. But after June, one particular date has multiple entries. That is because on a single day, they are trying to give the different cases for different states. But before June, they didn't really have that thing. For one, if there, it was overall India data set. So now I want to make this data set uniform. That is, on a single day, I want only one particular value, which is the total India cases, and not segregated state-wise. So that is why I have to group by state. And after doing that, finally, I will have my data set, which is going to be like this with the three columns of infected, death, and recovered. And yes, this one. And then what I'm going to do, there are again few functions that I've written. There's doc string and all of this, which you can understand what is this function really doing. And first of all, the show trend, wherein when I talked about FB Prophet, that library is used over here. Why? Because we're trying to understand the trend in this. So we'll be using the functions in FB Prophet, which helps us do that. We'll be specifying our changeover points also. So like when I use this for the infected, you can see this is the trend in which the infected number of cases are going on. Okay, and obviously we know that it is an exponential curve. Here it is seen like this because it's a logarithmic scale. And the dotted red line shows when the values are changing, the trend is changing. When I say the trend changing, that is basically like when it is infection. So how the contact rate is changing. So for this period, there will be a different contact rate, that is beta value. This can have a different, and that way. I mean, it's not a constant value. With time, these parameters that I talked about initially are also changing. Same will visualize for the recovered as well as the death. And so like I told you cannot I mean, so now the challenge over here is to find what are the values of these beta, gamma, and all these parameters that I described. So for that, we'll have to do some kind of an estimation, or that is why we are using this Optuna library called hyperparameter optimization. So for the hyperparameter optimization purpose, when we'll be feeding the current data, current India data, and try to come up with most likely, I mean, not accurate, but somewhere around rough approximate or rough estimate of these values that could be possible. So for that, we'll have to define our start period. So we'll be considering this dotted line, like which is somewhere around 10th of May. Let's say that as our that is from there on, we'll take the data, and the data which is there behind 10th of May, we are not going to consider for our optimizing these values, because that will just confuse, because the parameters are different. It's not I mean, we'll try to do with the latest data. So this is like a continuous process. Every day you have to tweak your model. Every day you have to see what is changing. You cannot just do it once and then that is the end of this epidemic modeling. It's not like that. Every day scenarios change, which we are also observing. After that, there's again a plotting function. And here, so susceptible is sum of infected, recovered, and dead. So because my data didn't have a susceptible column separately, so this function I'm just creating that column over here. And then this is a simulation which is like, earlier I used that ODE int function. Here I'm using a similar function called solve IVP, which is also there in SciPy. It is a newer function, and it's easier to use in the scenario. That is why I use this, but otherwise it does the same, same thing of solving the ordinary differential equation. Not going into details of this. Then there is estimator class, wherein this is where all that parameters that I talked about will be estimated. Giving so what are we giving? Our current data, and it will try to estimate and come up with the most likely some the parameter which we can safely assume and do our predictions with. So yeah, and so I mean there are different functions in this class. I've written different functions, and every function is doing one particular task, which is like the good coding practice. I'll just emphasize this part where tuna library is used and the function create study. You can read about it, and what we are doing is our task is to minimize objective functions that will be specifying, and pruner is used in order to avoid overfitting. There are different kind of pruners. You can experiment with that also. And we'll be defining our objective function in objective function, then how the error is calculated. So be writing a function for plotting the graph, comparing the values, comparing the estimated and observed values. Sorry, observed and estimated and observed values, and all of that. So then here is where it's a model. This is the base model class. This is where this is a base class, and you can just inherit this class and define your own model. So now what I'm doing for India is an SIRD model where I've removed expose for now. So this is the kind of relation. Removing expose, rest of the thing remains same. These are the 4 compartments. For simplicity, SYN into beta I've considered that as a row, only one parameter. Rho into alpha I've taken as kappa, and this thing as sigma. So there are 3 parameters that we need to estimate. And that ordinary differential equation, we'll be writing it over. I've also changed the variables. So X is now susceptible, Y is infected, Z is denoted by recovered, and W is dead or fatal. If you want to use a different compartmental model, I mean, adding more compartments, this is where you will change your ordinary differential equation, and likewise the other things which follows. It's fairly intuitive. You can just go through it. And here is a predictor class wherein you'll be, predicting what all, from the given parameters that we have estimated would be the future looking like. What are the cases that would be in future? So that is about it. So given the time constraint, I'm not running any of these cells. So now we'll be just, like I told, we'll be using 10th May data on or from 10th May onwards. That is what I've specified as start date, and population is something around this. And that estimator class, so we'll be using that, and the model is SIRD, and we'll be feeding all these parameters, population. Then India is basically the data frame name, which I had created above, and the start date. And then there was a function called run that class, so dot run. If we do, and when we do that, the experiment will be executed, and then dot compare, which is another function. If we run that, we'll see these comparisons between the observed and estimated values. So like you see here, the Y is infected, Z is recovered, and W is dead. And the observed and estimated values are, orange is the estimated, blue is the observed. They're almost coinciding, so we can, this is like a reassurance that okay, the values or the parameters that are estimated are okay or good to use. So that's about it. And so what are the value, or what are the parameters that are estimated? If you print that out, you can see these are the different values. Like you see this R naught, which is the reproduction number, which is 1.51 is what this is giving. Then you can predict, and this is how the graph looks like. Now the question is, how do you interpret this graph? If you see, I mean, this orange, which is the infected, is showing that peak is going to come somewhere early next year. Don't take this for an answer, because this is, it's a very simple model that I've used, only with 4 compartments, and a lot of things are like an assumption also. This is not the way it's going to be. And another thing to keep in mind is I've done for India. Now, we also have observed that India is such a diverse country. Every state, in fact, every district within the state has its own dynamic. So you cannot really take India as a whole. So you'll have to go for localized models to get a better idea of how this whole disease is spreading. So for that, I mean, this is a Ken article which I had read. In my previous talk also, I talked about this article because I really find it very relevant. So what it says is that early mathematical models for COVID-19 came with an expiry date. Now, post-lockdown, preparation is best left to localized models that account for cities' unique characteristics. Why, for giving an example of why it comes with an expiry date. So when I began this experiment for myself to understand this whole scenario better, when I started, I did it in the early March or somewhere there. And that time, this is the curve that I was getting, which tells that June or July is when the peak is going to arise. And we are already in June, July, and the peak we have not yet seen. So we cannot, I mean, this prediction that I had done earlier has totally expired. And that time also, again, the data was, just evolving. We didn't have that much of data. So all that parameters and everything, to start with, I started with a huge R naught value also. But now it seems like the R naught is also coming into some stabilization. So that is about it. So, mathematical models are useful. They help in planning for medical facilities, and in the case of COVID-19, guidance for lockdown implementation. But a number of early models predicted case numbers much worse than what we see today, but they were useful predicting the disease wasn't going away anytime soon. So this is where the importance of these epidemic model, comes in, because although they are not giving us accurate results, but it gives us some kind of an idea. So, for example, analogy like, pilots go and use this flight simulators so that they don't crash the airplanes. Same way, epidemiologists will use these kind of epidemic simulators to not to crash what, say, humanity or something. This is something I read somewhere. I found it very relevant. Again, so a number of models are in works, but without access to data and an active collaboration with government task forces, the utility is very limited. There's another model, apart from compartmental model, there's another agent-based model, which is based on reinforcement learning. It is even more complex, because you model the entire city in that, and every person is like an agent, where you model how the movement of these people is. So it's again very complex. That is another. I introduce this just to give an overview or an idea that this is another way of doing this or dealing with the situation. So that is about it. These are different. So again, I have no background in epidemics or anything. When this whole COVID-19 started, because of my interest, I studied it on my own, and these are the different resources that I took help from. So a lot of things that you see in my Google Colab will be from here and there itself. And yeah, so for a bonus, this is something again very useful I found. Like I talked about the flight simulator. This is the epidemic simulator. You can go and play around with it, and you can just check out this website. It's pretty cool. Why is it not loading? So anyway, I've come to the end of my talk. I can take any questions.
Yeah, we have a few questions for you. How can we improve the statistics part?
We can stop sharing. Yeah. Can we improve statistic part?
Yeah.
What is statistic?
I think he
part
meant
actually?
how
I
to
don't
study statistics.
Sorry,
Some
what?
resources on studying statistics, like how do you study that?
How
Like
do we study statistics?
some resources, like I can suggest ISLR is a very good book, Introduction to Statistical Learning. You can definitely go through University of Pennsylvania statistical courses. It's very basic. Begin from hypothesis of testing, go on all the way till regression, linear regression, logistic regression. That should really get you started with statistics. Karthika, any other resources? Please feel free.
Yeah, I think in general maths and all, these Stanford and all these universities have their YouTube lectures, so even that will be helpful.
Yeah, okay, I think that's it. There are no other questions. You've already shared the materials and everything. Yeah, thank
Yeah.
you, ma'am.
Thanks a lot. Thanks for the opportunity. I hope it was not like a overloaded kind of a thing for all y'all. Thanks for
No,
watching.
not at all.
Yeah, thank you for the opportunity.
Thank you. Thank you so much. Yeah, so let's move on. We have our last speaker for the day. We have Remya P. Vava, and she's a solutions architect at Qburst Technologies. And she will be talking about building a fault tolerant architecture. And welcome, ma'am.
Yeah, so hello everyone. First of all, thank you so much, Women in Machine Learning and Data Science Mysore chapter, for inviting me today, and thanks everyone for joining us. So let me introduce myself. I am Remya. I work as an architect at Qburst Technologies, and I'm a Women Technical Ambassador. I manage the WTM Trivandrum chapter, and I am also an I am Remarkable Facilitator. So today I'm here to talk about the essential factors that needs to consider while building a fault tolerant system. So let's start right away. So we all are familiar with using cloud services, right? And as developers, we run a number of services in the cloud on our day-to-day coding. So there could be situations where on a weekend when you are out for a movie and while enjoying the movie, how do you feel receiving a call in between with a notification that the application you just deployed or developed to production is down and the users can't access your application? So after receiving such a call, you never know what could be waiting for you on the other end. It could be outage of servers, multiple servers, frustrated clients, customers not able to access the web service. So most of the times, trust me, it won't be a false alarm. Immediately, we need to set up a war room. War room, struggling to understand the cause of the problem. So, multiple services, could be failing simultaneously. Also, we would be trying to restart the services, and after a few seconds of hope, the problem might come back again. So I'm sure that some of you may have already experiences like this, and you would agree with me when I say that these experiences are not at all pleasant. So a fault in one of the components of the system could be triggering a chain reaction that could be causing the unavailability of the whole systems. So we all know this problem very well, and we even have a name for it. We would immediately say that our system is not at all fault tolerant. So these activities should be compatible, right? The film we are watching or the weekend we are spending and the application we have built. So let's find out how to make this possible. So fault tolerance is nothing but the property of the system that enables it to continue to operate even when a fault occurs in one of the components. So the system continues to operate under every possible circumstances. So what is a fault? A fault is nothing but a deviation from the normal state. A fault can have many causes. Some of them are internal causes like a server outage, and some of them are external, like a sudden increase in the traffic. So in any case, the fault only affects on the internal state of the system. So it is not observable from the outside. Only when the problem bubbles up to the surface, there is a failure. So there's two typical failure modes in cloud services. That's total or partial unavailability. So these failures could cause business to lose money. They can also damage the reputation, for high profile service failures. It can be a trending topic, so we clearly want to avoid failures. So let's find out how we can do it. Well, you can think that the failures are the outcomes of faults. So then we could just, go and prevent the failures by limiting all the faults, right? That makes to sense, right? But unfortunately, that is not actually realistic. The truth is that due to the technical and economical reasons, it makes it impossible to prevent all failures. So, for example, down to earth, we cannot build a hard drive that lasts forever, or say a reliable network that lasts all the time, or we can't even build a 100% bug-free application or software. So we must approach this from a different angle. So we must acknowledge that everything may fail and will fail. So we must focus on not on preventing them, but preventing them from escalating into a system-wide failure. So unfortunately, we cannot build availability into our systems because availability is a derived property and not one that we actually directly control. But fortunately, there are other properties that we can control with our decisions on how to implement or like design a system. So one of those properties is fault tolerance. And key to obtain the fault tolerance is through stability. So when I say stability, the systems can be classified into two. That's a stable system and an unstable system. So the stable system resists small deviations but tends to return to its initial state easily. On the other hand, unstable system can be permanently pushed out to its, of its normal state even by a small deviation. So before going to further details, I would like to introduce these two terms, that's high availability and fault tolerance. So in the world of computing or cloud computing, these terms are actually given a lot of importance. One of the major factors of moving most of our workloads to cloud is because of the inbuilt fault tolerance and high availability features these cloud providers actually provide, whether it is AWS, GCP, or Azure. So these two terms are used very often, and like we want to create a high availability system, like we want to create a fault tolerance system. But both seems same, right? In the high availability system, you would expect that your system is always available. Your application would never go down. Same is the case of fault tolerance. So if your system goes down, it should come up automatically. Both sounds quite similar. So what is the difference between the two? There's a very thin line between these two. Both of them provide the same functionality with a little bit of difference. So let's find out what is that small difference. Suppose you are running this application inside this instance. High availability means if your server is down, your application should be available. So to achieve this, you will have to run one more server with the same application. So when the server goes down, this server will goes up. So something like this. So this once goes down, the end users will automatically point towards the other server. So in the event of failure, this users will be pointed to this server. Now to do this migration or switch from server to server, this might actually take some time. So this might have a very minor or a little amount of downtime, maybe for a few seconds or maybe for a few milliseconds. So that is high availability. You have your application on multiple servers. So when they went off, failure of one server, other server will respond to the users. The catch here is that it might take some time to do this failover. End users will face a little bit of downtime. Fault tolerance comes into picture. Here's where fault tolerance comes into picture. There's not at all, any downtime at all. So not even for a couple of seconds. Fault tolerance system is a system which is built to provide uptime for all the time. That is, I would say, SLA would be 100%. There won't be any downtime at all. So we have two servers with the same application running. So in case of any fault, the system, the end users will be directed to the both machines. So in maybe we can say that in a round robin fashion or in a weightage fashion. So in the event of a failure of one server, all users will be connected to the other server. They will be redirected. So basically your server is not down. Of course, the log will be increased in the other server, but still your application or system is never down. So that is what the thin line I was actually talking about. So this is another example to get a clear idea on what exactly is the difference between fault tolerance and high availability. So a twin engine airplane is a fault tolerant system. So if one engine fails, the other one automatically kicks in, allowing the plane to actually continue flying. Conversely, I would say a car with a spare tire is highly available. So a flat tire might cause the car to stop, but downtime is minimal because the tire can easily be replaced. As you can see, in a high availability system, we might have a very minor or little amount of time, but when it fault tolerance comes into the picture, you do not need any downtime at all, not even for a couple of seconds. So in this talk, I'm gonna talk about a few techniques that you can apply to build fault tolerant systems. And using these techniques, if you work with cloud services, you can make them more fault tolerant. So I'll just quickly go through the first one. The first and the most basic is to contain the fault. So the idea is actually very simple. Introduce physical and logical barriers to reduce the blast radius of the fault. Say, for example, if you look in real life, there is an example, fireproof doors. So this will prevent the fire from propagating to other places, or at least they will slow down the propagation, right? So giving people more time to save lives. So in computing, a containment applies to both hardware and software. Sorry. Say, for example, in a data center, we have multiple networks for different classes of networks. So there's a network for production traffic, there's another one for backups. So these days, for any cloud services that runs in multiple computing nodes, a load balancer always sits in front of the cluster, and it distributes the traffics among the nodes. And the load balancer can also monitor the health of the nodes, and it can actually restart or replace the faulty nodes. So in that way, if one of your servers goes down, only that server will be affected, but the service will continue to provide. And containment also applies to the logical resources inside our application. For example, a main applications uses thread pool to manage concurrency. So that is very common. If your app has a single thread pool, and if one part of the applications becomes slower, the threads will inevitably concentrate there. So instead, you can actually have multiple thread pools for different kinds of tasks. Consider having a separate connection pool for maybe each dependency. So that might reduces the efficiency of the service, but in exchange, it actually increases robustness. So the next one is the choice of communication mode. It also affects fault tolerance. There are actually two communication modes, synchronous and asynchronous. Synchronous communication, where you require both sender and receiver to be available at the same time. So if the receiver is not available, the message cannot be delivered, and that propagates the fault from the receiver to the sender. Whereas in asynchronous communication mode, it decouples actually the availability of sender and receiver. So in this case, if the server is not available, the message is put in a queue and the sender is not at all affected. Moreover, when the receiver recovers, it can catch up with the backlog of queued messages. So for example, there are technologies to implement this, queues like RabbitMQ, SQS, and all. So these are available in almost all of the cloud providers. So how to contain the faults? Obviously, invest in redundancy. I would say, just as an example, even the space shuttle used to fly with 5 expensive redundant computers. So for a fraction of that cost, you can have multiple computing nodes behind a load balancer. So that was the first techniques, contain the fault. So the next one is fail fast. A quick error is always better than a slow response. So that might sound a bit confusing. If some part of the application is being slow, you would think that wouldn't it be better to give it more time rather than giving up? But in practice, these errors and slowness are actually correlated. So if something is taking longer than usual, chances are high that they may fail anyway. So waiting will be in vain. But more importantly, waiting is one of the worst things we can do, because it obviously reduces our options. So instead, if something fails fast, we have many options at our disposal, like aborting or retrying, or maybe activating an alternate path. So even when some part of the system fails, system as a whole may still be able to deliver value, but only if we actually react quickly. So there are actually multiple techniques to do this. First one is early validation. Say, for example, it's pointless to start processing a transaction, acquiring the necessary connection with database, only to discover later that the transaction cannot be completed due to some minor errors. So do not leave validation to the database, always push it towards to the API of your service. So the next one is reject politely. Look for opportunities to turn back request without doing much work. So if you are writing a REST service, you should return 400 request status, status code back for an invalid request. I would say we can actually go one step further. You could think of reacting not only for invalid request, but for a valid request when the system is actually under stress. So your service could detect this by measuring the length of its queues. As I mentioned earlier, there will be queues to manage the polls, or maybe you can manage it by the usage of polls, measuring the length of polls. So in that case, you could immediately reject additional traffic. And when we reject such a request due to overload, remember to return with the proper status code. And the last technique is never wait too long. In my experience, lack of strict timeouts is a main contributor of cascading failures. The general rule is very simple. Any operation that is slow or blocking must have a timeout. The shorter, the better. So never, never, never wait indefinitely. So setting timeouts is probably the simplest way we have to make our system fault tolerant. So just remember every line of code when we write, think whether it's going to be a potentially slow operation and make sure that we set up a timeout to run that. So to summarize how to fail fast, quick error is often preferable over a slow response. The next one is look for opportunities to turn back request before doing much work. Do not hesitate to refuse the service when in trouble. And most importantly, remember to set timeouts around anything that may take more than an instant. And the next one is escape, that is stay away from trouble. Let's borrow these ideas from circuit breakers. Say, for example, we have the circuit breaker at our home, right? They have two positions like open and close. Normally they are close. That means they connect the wiring of home to the grid. So whenever there is an overload, they automatically switch back to open positions and to protect the rest of the component from overload. So we can just borrow this idea and we can apply this specifically in the integration points like REST APIs. Imagine we have a client and server and we installed a circuit breaker between them. So normally it will be in the closed position and all the requests will flow from client to server. Circuit breaker will just sit there in between them and it will be actually monitoring the request from client to server. So however, if the server becomes unavailable or slow, these requests will be starting, failing. So the circuit breaker will detect that whenever the error ratio exceeds a configurable threshold. We can actually configure this threshold. So whenever this error ratio exceeds this threshold, the circuit breaker will switch to the open position. And when in open position, it will immediately interrupt and make all the requests fail from client to server. So that has the benefit for both client and server. And, these circuit breaker patterns are available in most of the cloud platforms. And one example is like fault tolerance library. So most popular one is Hystrix by Netflix. To set up the timeouts, fallbacks, and monitoring. The last one is monitoring and alerting. So we can actually configure fallbacks behavior. So instead of just failing the request, you can just return the fault value or a cache value, or you can actually activate an alternate path. So that's the one, escape the trouble. That's it. How to escape it, detect the problems, anticipate the failure, and degrade, gracefully. And the next technique is would be to adjust. So anywhere where an interaction takes place, the parties should communicate their expectations and should keep each other updated about their status. So a good example would be the TCP protocol. So when two internet hosts wants to open a connection, they follow a three-way handshake protocol. which allow them to agree that, okay, they are ready to exchange info. And then once the connection is open, these parties dynamically negotiate a TCP window, that is, number of packets that can be flight at any given moment. So if the receiver is congested, it will reduce automatically, it will reduce the size of the window. So we can apply this idea to not only to network protocols, but also to the application layer. For example, set the limit for fetching the database results. Patiently the boundaries. The concept here is unexpectedly large data is always a threat for the application and the database. Another powerful technique is streaming of those responses. Streaming can be used with both the databases and with REST API, that optimizes both memory consumption and latency. And as our application grow, they tend to accumulate resources like resource base, memory. Sometimes accumulation is actually part of a normal operation, like populating caches or keeping the log files for an audit trial or something. So in those cases, it is our responsibility to design mechanisms to keep the size of those things under control. Say, for example, evicting caches, or maybe you can actually rotate the log files. So in some cases, accumulation of resources are unintended, like a memory leak, a hash map, or a result of a bug. So just make sure that you always set limits to any data sets that may grow. The next one is flow control. The flow control allows the parties to dynamically adjust the speed of the communication to their current needs. So these REST services can, for example, push back to the client by rate limiting or maybe a request locking. So if you have a producer and a consumer and they work at a different needs, you can smoothly difference it by adding a buffer, but make sure that the buffer has a limited size. Negotiate the speed. If you are running in cloud, you can use outer scaling to dynamically adjust and match the capacity of consumer and producers. The last one over here is retries. Again, the idea is very simple. Insist a few times before giving up. However, it is notoriously difficult to implement retries correctly. And unfortunately, poor implementation of retries decreases stability instead of increasing it. So firstly, it's not okay to retry every possible error. There are actually transient errors and permanent errors. So if you are working with REST APIs, those are roughly described by their 500 and 400 family of status code. So it is okay to retry after a transient error, but it is pointless to retry a permanent error. So retrying an error until the operation succeeds is obviously a recipe for disaster. So instead, the caller should back off and it gives the system a chance to recover. And the final one is learn. No matter how well your system is designed, its ultimate benchmark is how well it behaves in production, right? So once you have deployed your services to production, you must collect metrics about its behavior to understand how actually it's doing and how many transactions it's processing, what is the response time, how many nodes are there in the cluster, and how many of them are actually healthy. So the most important metrics is you must calculate the availability and reliability of the services. So get that information displayed in your dashboard, analyze the strength and analyze and set up the alerts. So the next one is how to test your system is actually fault tolerant. So I know you may be already convinced now the need to make your service more fault tolerant. But how do you test indeed, your service is actually fault tolerant? Well, you could actually deploy to production and just wait for the next outage of your cloud provider to see and discover if you have done your homework correct. But a smarter way is to test continuously, instead waiting for everything fails in production, you can actually introduce bends to environment. So this is known as chaos engineering. So, and one prominent tool in this area are Chaos Monkey, which randomly destroys the nodes in the cluster. So you can get a chance to test the application if it is whether fault tolerant or not. And the final one is to learn. In any case, despite of all our efforts, things will always, inevitably fall in production. So we can see each incident as an opportunity to learn. So learn from mistakes, consider it as an opportunity to learn. So this is going to be my final slide. Life starts after releasing version 1.0. So the reality of most of the software is that the life happens after the initial release. So we must prepare and invest for the long term. So the main takeaways I would say is that we cannot prevent all failures, no matter how long the probability of an event. If it is not zero, it will actually eventually happen. So instead, focus on preventing those faults from escalating into a disaster. So when you run system in production, I would say your quality of life after the release 1.0 directly depends upon the robustness and stability of your system. So when you build those properties of your system and properly, you will be able to enjoy your movie night without interruptions. So that is it. Thanks everyone again. I hope you have enjoyed the session and you have got your takeaways. So back to you, Srishti.
Yeah, thank you so much. That was a great presentation. Yeah, so we have a few questions for you.
Yeah, sure.
Yeah. So we have a first question from Julian, ma'am. If we were to schedule consumers for peak time and non-peak time using Rabbit MQ, how would we design the system?
Yeah, so if we were to schedule consumers for peak time and non-peak time using RabbitMQ, how would we design the system? So I would say you can, in the message queues, we can actually configure it. The main idea is to separate all the dependency tasks and to separate it to, most efficiently into different connection pools. So we can actually configure it accordingly. And it's not just RabbitMQ. In any message queues, we can actually configure it. I don't know if you are looking for more detail. Maybe I can get back to you if you're looking for more details.
Yeah, so we have another question from her. Can we use hysteric circuit breaker in AWS? Which cloud did you use in it?
Yes, historic circuit breakers, that is by Netflix, but the circuit breaker patterns are available in AWS. So it doesn't depend upon a particular tool. It is actually a pattern. So in AWS, it is going to be a different architecture, and in GCP, it's going to be a different architecture. It's important that how we actually architect it to match with that pattern. So the circuit breaker patterns are available in AWS as well as in GCP. So not just historics. I just mention it as an example.
Yeah, so we have our next question. Please explain about fault.
Yeah, all right. So, as I first mentioned, we can actually say that fault is nothing but it's actually a deviation from the normal state. So, I would say it can be anything like a server outage. That is actually an internal fault, or maybe a sudden increase in traffic, which would keep a server down. So any behavior from a deviation of a normal state, we would call it as a fault. So, and as I mentioned, fault only affects the internal state of the system. So it is not actually observable from the outside. So only when the problem rises and it reaches the surface and it causes a failure, that is only when it is visible from the external side. So fault is nothing but a deviation from the normal state. It can be anything. It can be external. It can be internal.
Okay, so we have a last question. Would you say building a fault tolerant system would end up in increasing the infra cost?
Yeah, definitely. It would cost, a bit more than the normal design. I have actually mentioned an example like, instead of having a damage to our reputation instead of having a frustrated customers. So we definitely that cost is definitely better. But I would say not all applications should be made as a fault tolerant, right? There are certain applications where not even a millisecond downtime is not acceptable. So there are applications where actually downtime of the system is acceptable. We can actually do the deployment in non-office hours or non-working hours at midnight and all. But there are applications where even a millisecond of downtime is not acceptable. So you have to consider building a fault tolerant, high availability system to only those applications. So, and definitely the answer to your question is it would goes infra cost, because we have to do the circuit breaker patterns, you have to introduce load balancer, you have to enable the auto scaling mechanism. So definitely that would cost extra infra cost.
Thank you, Ramya ma'am. Thank you, Julian ma'am. Yeah, so I guess that's it. We are done. No more questions. Okay, so let's wrap the session up. I thank you all the speakers for joining us today, and thank you to the audience as well. And I hope you all like the session today. Do join us for our future events. We have a lot in store for you. And so, yeah, this is the end. Thank you again. Thank you, everyone.